I hope it's going to focus. Yeah, it seems to focus. Okay, so we're going to start by considering a really basic question in mathematics, which is, what does it mean to count something? Okay, so this is so basic that people didn't ask it for the first several thousand years of mathematics. But what does it mean to count? So now people, so Cantor, this guy, George, I don't know how, I'm going to say George, but I think there's no, it's like Georg or something. He's German. Was German. So he said, okay, what does it mean to count something? It means to put something into a bijection with the positive integers. Let's go with that. I'm not sure if he said exactly that, but let's go with this idea of a bijection. So if I have my class, my rather tiny class of students, so it's in particular a subset of the positive integers, like a prefix, let's say, of the positive integers. So I have 9 students. I would say, okay, 1, 2, 3, 4, 5, and so on, right? So you establish so you have a first one, you have a second one, you have a third one, and we may not care about the order of these things. It's not like I'm saying the tallest student, the second tallest student. Like, I just want to count the students, so I want to say, okay, you, you're 1, you, you're 2, you, you're 3. So whatever, we don't care about the order. Okay. So do we accept that counting means, I get this, so it's a bijection to 1, 2, 3, 4, and then at some point, if I've got an infinite set that I'm counting, then I can go on forever. If I've got a finite set, I can go 1, 2, 3, 4, 5, blah, 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 11, and then I'm done. Okay? So that's a bijection to something. So bijection means it's 1 to 1 and onto, and in this case, I can only make it onto if it's a finite set I'm counting. I can only make it onto by taking a prefix. If it's an infinite set, then I can make it onto all of the positive integers. Okay. So do we believe that this is what counting means? 1, 2, 3, 4, so on. Okay? Any objections? Okay, so if you believe me so far, that's good, because it took a while for people. So like I said, if you have, I have 3 overhead markers. Actually, I have more over there, but I have 1, 2, 3. Okay, I have counted them. I have said this is 1, like whatever order they were in. This is 2, this is 3. So there, I've established this bijection to this subset. Okay, so if you can establish this relationship, then we're going to say that the set, if you know, this is the set of overhead markers, it is countable. I can establish this bijection. I can say this is 1, this is 2, this is 3. Okay. If I had an infinite set of these, it would still be countable, because if I could establish such a relationship, I could say this is 1, this is 2, this is 3. So let's consider some infinite sets that are countable. What about the positive even numbers? What is the obvious way to map the positive even numbers to the positive numbers? Well, you divide by 2. So you say, okay, 2 is the first one, 4 is the second one, 6 is the third one, 8 is the fourth one, right? So you say, okay, then if you give me any, I have a way of enumerating these things. If I could write a little program that would list these numbers, and eventually for any positive even number, it's going to hit it. Right? So the positive even numbers are countable. it's an infinite set, but it's countably infinite. I didn't start the timer. I may get a grocery delivery at some point during this lecture. I will just sort of answer the phone and tell Terry, the delivery guy, that yes, I will be down after the lecture. Okay, so even numbers are countably infinite. Everybody believes that. I hate not being able to see students. Okay, so what about all of the integers? Okay, well, what we can do is we can say 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4. Okay? Does every so what is my procedure? It is I can say there's this little program for I equals, okay, so print 0 for I equals 1 to infinity, print I, print minus I, and 4. Does everyone believe that this little program, for any integer you care to think of, eventually this will print it? Okay, what would be the problem if I said, okay, I'm going to first list the positive integers and then list the negative integers? Instead of interleaving them like this, I'd be say, okay, well, print 0 for I equals 1 to infinity, print I, and 4 for I equals 1 to infinity, print negative I, and 4. What's the problem with this program? Yes, this is never going to stop. So if you tell me, okay, well, will this ever print negative 1? No, it won't. Because this is never going to stop either. But for any number you name, it's going to hit it eventually. Here, if you said minus 1, it's never going to hit minus 1. So this is not what we want to do. So, but because this program exists, the integers are countably infinite. Okay? The positive integers are countably infinite. The positive even numbers are countably infinite. The integers are countably infinite. What about rationals? Okay? So any finite set is countably infinite, right? Because you choose some order and then, but so from now on we're only going to care about infinite sets. Okay, for the rest of this class. I mean, all that finite stuff, that's too easy. We want hard stuff. We want infinite. So what about, now I just showed you that stuff about this program works, this program doesn't work, because you have to think about that for the, when you do the rationals. Okay. Now the rationals also, you have to be a bit careful. Oh, wait, there is a question. Yeah, okay. So let's only consider the rationals between 0 and 1. Well, actually, let's exclude 0. Yeah, let's exclude 0. It doesn't matter, but let's exclude 0. So we're looking at rationals in 0, and I'm going to include 1. So this notation, if it's an open bracket, I've been using this in the assignments and everything. If it's an open bracket, it means it excludes this endpoint, and if it's a closed bracket, it means it includes it. Okay. So I want to show that these are countably infinite. So what I'm going to do is say for, actually I'm just going to check that code is still off. Let me grab my cup of, yes I did, good. Now you're going to see why I say for j equals 1 to, no, I'm not going to do it that way. I'm going to say I. For I equals 1 to infinity, for j equals 1 to I, if, do people prefer angle brackets or so this means greatest common denominator. So how would you check this? You check this with Euclid's algorithm. So do people prefer if I write GCD or I can write angle brackets? Print, this is why I was messing around with the order. Print J over I. Okay? And if, and for, and for. Okay, so what's angles? Good, good, good. Okay, so what's this going to do? Well, I is 1, j is 1, it's going to print 1. Then I is 2, j is 1, it's going to print, and the greatest common divisor of I and j is 1. So it's going to print 1/2. Then I is 2, j is 2, but now the GCD, the greatest common divisor, is 2, it's not 1. This, okay, if it's in C, this would be a double equals. And so it's not going to print 2 over 2, because 2 over 2 is 1. Okay, so we've already covered that. So now I is 3, it's going to print 1 over 3, 2 over 3. It's not going to print 3 over 3 because GCD of 3 and 3 is not 1. Okay, then it's going to print 1 over 4. It's not going to print 2 over 4 because 2 over 4 is 1/2. The GCD is not 1. So then it's going to print 3 over 4, 4 over 4, no. Then it's going to 1 over 5, 2 over 5, blah, blah, blah. Okay, so if you pick a rational number between 0 and 1, not including 0, then you can tell it to me in some ratio A, B, where A and B are positive numbers, and you can put it in its simplest form where it's A and B have no common divisor. So this is the GCD of A and B is 1. And then I can tell you, this is recording. I can tell you an upper bound on how many steps my program will execute before it prints your number A over B. Now, I would have to work out how many times it skips numbers to actually figure out which rank it's going to assign A over B. And notice that these things are not listed in increasing order. Right? You go from 2/3 and then you drop down to 1/4. There's a reason for doing it that way. because we have to, sort of. But do you believe that this is showing, this, for any rational number between 0 and 1, you tell me as a ratio, and I can tell you an upper bound on when my program is going to print that number. So this means that, and of course the 0 and 1 is not actually a problem. If I'm a little bit careful, I can actually make it do all of the rationals. I just have to be a bit sneaky, because I don't want to, I have to be careful and do this dovetailing, interleaving thing a bit more carefully so that it can keep going. So what's the problem if I said something like, if I wanted to list them in increasing order, I would be saying, okay, well, for if I wanted to list them in increasing order, then I would want to start with the smallest denominator, but there is no smallest denominator. So you sort of get that problem that you had up here, where you'd be saying, okay, any questions? No questions? So people believe that the rationals between 0 and 1 are countably infinite. Is anybody still there? Okay. So that's fine. I mean, that's establishing this nice bijection. Now, so where does the problem come? Well, not all sets are countably infinite. Yes. Have you seen this? Okay, so I'm starting with this because when we talk about the halting problem, people keep saying diagonalization. And it's a proof by contradiction. And you keep thinking, like, why is it called a diagonalization? What's diagonal about this? And the reason it's called a diagonalization is you see that if you see Cantor's proof that the reals are uncountably infinite. Okay, and so some of this is not a surprise to some people. So now, so the rationals in this interval are countably infinite. Now we're going to say, so the rationals are countably infinite, but the reals are not countably infinite, they're uncountably infinite. So this is the kind of thing where if you go home and somebody says, what did you learn in school today? And you say, well, I learned that some infinities are countable and some infinities are not countable. And they're going to think, like, what do you mean an infinity is countable and not countable? So the reals in 0 to 1 are uncountably infinite. So this is a proof by contradiction. And so I think in some message, in some announcement, I referred to this as mathy judo, right? Because it's sort of a proof by contradiction is sort of, you assume something and then you use that assumption to reach a contradiction. So here it's like we assume somebody can do something that we think is impossible, and then we use that. Like in judo, you use your opponent's strength against them. Well, here we're going to say, okay, assume that you can do this, then I can use that there is an algorithm for doing this. I can build on your algorithm, use your algorithm as a subroutine to build an example that your thing can't work on. Okay, so what did Cantor do? He said, okay, so assume there is an ordering of the real numbers. So the real numbers, you can express a real number in this interval. No, actually now I want this to be slightly the other way. I want to include 0 and I want to exclude 1. Okay? It doesn't really change anything, but I'm just So now that we're not including 1, any real here can be expressed as 0.72158394, blah, blah, blah. Okay? And let's put some other 3 8s, 5 1 4 6 6 9 2, blah, blah, blah. And do these line up? Actually, more or less. Let's put the 9 over here, so it lines up a bit better. And 0.9849844, blah, blah, blah. Okay, so you can write any real as a 0 point and then some string of numbers. Maybe the real numbers are the friends we made along the way. This sounds like a quote. Okay, and that's that rings a bell. But if I stop and think about it, I'll lose track. Okay, and we still have quite a bit to get through today. So. Now notice that there's one thing about this, which is I'm not allowed to have 0.999. Actually, I'm not allowed to have something like even 31231299999. I'm not allowed to have an infinite string of 9s. That's the only thing I'm going to have to be careful about. Okay, I can have an infinite string of 8s. But if I have some number and then an infinite string of 9s, then this is actually 0.313000. And that's just because this and this are the same thing. And we don't write it this way, we write it this way. Okay? So I have to be a little bit careful. So, Cantor said, let's just write some more numbers. 2 1 7 7 4 5 3 1 2 and 0.15568888. Okay. Let's just write some numbers. So Cantor said, assume there were a bijection. So these kind of proofs of contradiction is where, so usually in mathematics we use the present indicative, right? You say, assume there is. So this, people didn't always do this. And I realized that one time I was in Italy and I thought, oh, well, look, there's Hardy's Mathematician's Apology in Italian. I thought, but it's a really small book. And I thought, I've read this. It's about mathematics. And I've read this in English, so I should be able to read this in Italian. Until I got to the proof that the root of 2 is irrational. And the thing is, then it didn't click when I read it in English, but everything is in the subjunctive and the conditional. So assume it were rational, then there would be a ratio A over B, blah, blah. And so that was actually beyond the level of Italian I could do. So assume there were. So suppose there were a bijection between the reals in this interval and the positive integer. So you could list. There would be a first one. There would be a first real, a second real, a third real, and you could write them out like this. So maybe this is the first real in this interval. So you could list them. Right? You could. I would have a little program that would generate these numbers, and so if you had that, so if you had an ordering, like if you had 1, 2, 3, if you could count these, then what you could do. I want this number to be No, actually, this is fine. Okay. Then you could construct a number that isn't in this list anywhere, right? So this list is going to go on for infinity, but the idea is for any real number you pick in this interval, at some point it appears in this list. It has to, it can't just not be there. Because that's like, with my little program for the rationals, for any number you pick, I can tell you that yes, it's in there, and in fact, I could work out that it has to be by this step. You tell me A and B, I can tell you based on A and B, I can tell you how an upper bound on how long we take to get there. So here, the idea is you could tell me any real in this interval, and I could tell you that yes, it has to be in this list. So Cantor's idea is you take the first digit here, right? So we're going to build this number that's not in the list, and it's going to be, so this list is infinitely long. I'm going to take the first digit of the first number in this list, and the first digit of this is not this digit. It is something other than this digit. So it could be a 5. Right? And now I take this 8, and this digit of the second digit, so I take the second digit of the second number, and then the second digit of this number I'm building is a 4. It's just something that's not an 8. Now I have to be a little bit careful because I don't want to build something like 0.5999999, because like I said, we wouldn't actually do that. So you just have to be careful not to ever hit a run of, like if you get a 6, you don't turn it into a 9. And then you get a 4, you don't turn it. So every so often, turn it into something that's not a 9, just so you don't get an infinite. That's the only thing you have to be careful about. This is a 4, so this is not a 4, it's a 7. This is a 7, so this can be a 6. This is 1, 2, 3, 4, 5. This is an 8. So this can be a 9. I just can't have an infinite string of 9s. Okay, so that's how I build my number. Now, what property does this number have? It differs on the first digit from the first number. It differs from the second digit on the second number. It differs from the third digit. In the third digit, its third digit differs from the third digit of the third number, right? So if this number were in here, somewhere, we're in the list, it was ith in the list, it was 102nd in the list, well, it can't be, because it would differ from the 102nd on the 102nd digit. So for any number in this list, this is not equal to that, because it differs from the ith number on the ith digit. So I've just constructed a number. This list, infinite though it may be, this infinite list is supposed to contain all of these reals, but I've just built one that isn't in there. And notice this is where you get this diagonal from, okay? Because this line is going diagonally, okay? So it's mathy judo. It's a proof by contradiction. We assume that there exists this bijection between the reals in this interval and the positive integers, and then based on that assumption we could construct a number that we missed. Okay, so that's the proof that the reals in this interval are not countably infinite. They're uncountably infinite. Now you can go a lot deeper into this and get into, like, is there an infinity between the countable infinity and the infinity of the reals? And I think then you get into like the continuum hypothesis and blah, blah, blah. We don't need that for this course. Okay, we actually don't need this, except it's a nice way to sort of get our heads around diagonalization and understand why it's called a diagonalization.